All right, thank you. So I'm Febo or Fernando. You're going to see me with different names, but if on my GitHub, you're going to see me as Febo. And I work at the dev tooling team at Anza. And today I'm going to talk about Pinocchio, how it can help you write more efficient programs, and go through a couple of examples. But first, I'm going to just give you a little bit of context what Pinocchio is and why it was created. So if we go back kind of like a year ago, you look at the Solana program crate, which was the main crate to write programs. It had many external dependencies. And what happens with that is that every time they went to build your program, those dependencies get pulled in, and it's kind of easy to end up with some dependency issues, as many of you might have done. And the funny thing is that many of these dependencies are not even used by the program. So they're just there. And so then, when I was at the Hacker House in London last year, had a chat with John, and the idea of having a dependency-free SDK to write programs came up. And that's how then Pinocchio was born. And the idea of Pinocchio is to be a program-first SDK that is going to follow what works best for on-chain programs. Meaning that even we're going to redefine types and functions to make it performant. And we are following a few principles building Pinocchio. So one of them is that we don't have external dependencies on the main crate. That is not to say that we're not going to use any external dependencies. The idea is external dependencies should be add-ons to the main crate. So you should choose to add them if you need that functionality. Or you can actually implement that functionality in a separate crate and you use that one instead. The idea is to avoid kind of like locking people with specific dependencies, so we mitigate dependency issues. The second principle, which is kind of like involve multiple items there, is really focus on performance. So the SDK, the main SDK, doesn't do any dynamic memory allocation, and in fact is a no STD crate, meaning that it doesn't use any of the STD types. And if your program also doesn't use any of the STD types, which is the Rust standard library, then the STD doesn't even get linked to your binary, which contributes to have smaller binaries. Also uses zero copy whatever is possible. So for instance, to access sysvars data, access them zero copy, which again is efficient in terms of CU, and provides safe and unsafe variants for functions. The idea here for the unsafe is to have a faster API for cases where developers can guarantee the safety constraints. So it has to be used carefully. So it's there as an option. It's definitely possible to write a program without any unsafe code. So I'm going to say one more time. It's possible to write a Pinocchio program without any unsafe code. So use it if you want that extra performance. Use it carefully, especially when you're borrowing account data, because then it's on you to do the borrow checker job. So how can we use Pinocchio? So use Pinocchio the same way they use Solana program. So use, instead of the Solana program crate, to use the Pinocchio crate. So here I'm going to talk three aspects that is going to help you write efficient programs with Pinocchio, and then I'm going to show you two examples. I don't have code examples here, so I'm just going to give you like how things work. But I do have some tables with some numbers to show you. So you know that every program has an entry point, and the entry point's job is to actually read the input given by the runtime and get the pieces of information that you need to execute your instruction, which mainly is the list of accounts and instruction data. And in Pinocchio, the accounts is actually represented as a single pointer referencing directly the information from this input. So there is no copies there. And then these references then are stored on a static allocated array, which is what it gets passed then to the program. And those two changes translates to a much more efficient entry point, and is basically an order of magnitude more efficient. And this is kind of like compute that is kind of like used even before your program starts executing an instruction. And in most of the time, your program doesn't have control with this because you added the entry point using one of the macros that actually adds that for you. So basically, it's something that, depending on which one you're using, you're not going to have much control of how much or how expensive it is. The second kind of like entry point that Pinocchio offers you is a new type of entry point, which is kind of like delays reading the input. At first, it doesn't do essentially nothing and gives it to you kind of like an object that you can then choose when to read and what to read and so on. And this is ideal for programs that either have a single instruction or they do just a single thing, or have very few instructions and you want control of when the parsing, the reading is going to happen and so on. And here I give you a little piece of code. That's the only piece of code that I have in the presentation, where is an OOP program, fully functional. So if you get this one, it compiles and it runs, which essentially has an empty processor. This is exactly how the no-op program is implemented. But this one takes only 2 CUs, and it has kind of like 900 bytes the size. If you look at the current one, it takes like 40 CUs, because it still goes through the kind of like the entry point that, although you don't get anything to kind of like read from, because there's no accounts and no instructional data, just the fact that you're checking that is actually consuming CUs. The other aspect that we have in Pinocchio is that it uses these lightweight view types. So it redefines the account info, the account meta, and the instruction. And instead of holding kind of own data on them, they hold references, which reduces the amount of cloning that happens. And the account info in particular also uses KV's efficient borrow checker and Dean's and Leo's efficient close account. So again, there are other savings that you get there by using these types. But one particular part that these types really help you in saving CUs and having your program more efficient is on CPIs, in cross-program invocations. And you can see here, this is a little comparison that, considering the base cost of a CPI, which is 1,000 invoke units, is a little bit more because there is a variant there that depends on how much instruction data and account size that you have. But to simplify, I just separated 1,000 invoke units, which is the fixed cost of a CPI. And then the second part of the cost is going to be mostly you creating these instructions, the account meta, objects, and so on. And those, because it gets cloned, it gets very expensive. But using the Pinocchio, then you can save a lot there, like kind of like 5x, more or less 4x, because you are reducing a lot the clone, because you're just using references instead. So that's where the gain comes, by reducing the amount of data that gets cloned on-chain. And the third aspect that I wanted to talk today was program logs. So program logs are expensive, and the cost of logging can be broken down in two parts. One is the base cost, which is either 100 CUs or the length of the message, whichever is higher, and the formatting cost. So we are talking about logging that involves formatting. And format is known to be heavy, is a super flexible process, but at the same time is complex. And so in Pinocchio, we re-implemented a way that you can format message using a lighter weight logger type with a companion log macro, which doesn't do any allocations, doesn't have any external dependencies, has some simple formatting, doesn't offer all the options, but it has some simple formatting there that you can define precision and width of values. But again, we can get some really good gains there on the formatting cost. As I said, the log, the 100 there, the base cost that's fixed, there's not much we can do because that's the cost of the syscope. But then you see the difference there. In some cases, is an order of magnitude better. In some other ones, it's kind of like 3x better. All right, so what sort of gains can you expect by using these things? So here I pull up two examples. So first of all is P-token, which is the reimplementation of the SPL token using Pinocchio. And the objective here was to decrease the amount of CU used by the token program, because if we manage to do that, we free up CUs for other transactions to be executed in the block. And in the end, we managed to reduce the CUs used by the token program by 88 to 95%, depending on the instruction that you are executing. Transfer, for instance, is like 5% only. And I think the one that uses multi-sigs is about like 12%. So this is why there's a variation there. But we managed to reduce, maintaining the same behavior and the same output. We managed to also reduce the binary size by 40%. And here is 40% considering only the original instructions, because we are also proposing to add 2 new instructions to the programs, which makes the final reduction a bit less than 40%. But the original is just 40% reduction there. And one interesting aspect that I wanted to mention is that 70% of that reduction is achieved by changing the entry point, to use Pinocchio entry point, and doing zero copy account data access. So basically ditching Borscht, bin code, anything that kind of like does copies. That is the big chunk of CUs that you can save. So with those 2 changes, you can make your program significantly more efficient. The remaining 30, then it was just like tinkering and making sure that we are doing exactly what we need, not extra checks and so on. So the plan now is to replace the SPL token by P token as described on CMD 266. And currently we are in the process of waiting the formal verification and audits. We completed tests. We run the fuzzing using the FireDancer tooling, and the program is behaving exactly the same. Well, it's the same, but using much less CUs. The second example that I want to give was more just to kind of like check how efficient we can it would make to use the lazy entry point. So we picked up the memo program, which was like an ideal example for a program that would benefit from the lazy program entry point, because the memo program just do one thing. It's just that the memos logs a memo to the ledger. And on the memo one, that we managed to reduce the CUs by 80 to 87%. Again, same behavior, same output, and everything. And here the reduction is kind of like in three aspects. One of them is the entry point, that is using the lazy entry point is much more efficient. The second aspect is using the logging from Pinocchio, which is more efficient to format the message because it logs the pub key of the signers. And also the way that we are actually generating converting the pub key to base 58 is using a more efficient library as well. So there's 3 aspects that kind of like represents that gain. So what is next now? We are currently working on integrating these new types into the Solana SDK. So it's going to make it easier for you to write code that, for instance, you need to use in an off-chain client and on your program. So you're going to see some new crates on the SDK coming up, which is going to include these types from Pinocchio. And we also are working on Pinocchio-fi other programs. So the ATA program is currently almost ready to review. And we already have plans to do similar optimizations on the token 22 as we did on P-token. So maybe it's going to be a P-token 22. I don't know. Maybe we can come up with a better name. So that's reached the end of my talk. I just want to take the opportunity to thank all the Pinocchio contributors, because people have been great, providing lots of support, lots of ideas, and lots of PRs as well. So keep them coming. And thank you.